Okay, so now officially, hello everyone, and welcome to my presentation about proactive Azure cost optimization based on machine learning. My name is Michał Romanowski, and I work at Allegro Pay, which I already mentioned is a payment method for an Allegro. I'm a DevOps engineer, and I work with Azure and Kubernetes stack on a daily basis. And to begin with, we are dealing with 6 clusters right now, which serves almost 60 nodes. And in addition to that, we have numerous Azure resources, which generates thousands of euro costs. So what's the problem with our environment? As you can imagine, the scale is quite big, and we've discovered that we are wasting money because of, let's say, not very wise reasons. This chart comes from the beginning of the year, when we discovered that one of our storage services generated huge costs out of nowhere, actually. And when we started to investigate this matter a little bit more, it appeared that this exact storage account has been changed to a higher SKU level. And as a matter of fact, we found out about this after a couple of days, when the storage account generated around 3,000 euro of unplanned costs. So this is quite a big amount. And the final question is that, what can we do about this to prevent this from happening in the future? So what are the possible solutions? The first thing that came to our mind was this Azure built-in feature called cost analysis. This chart comes from the Azure portal. This is the cost analysis tab in a resource overview pane. And as you can see here, we have some steadily rising costs and a monthly budget cap. And then hitting this budget cap triggers an alert, and we receive an email about it. The problem with that solution is that we are alerted after the cost is generated, and the North Star is to be notified before it happens. Like, obviously, because of the Azure internal billing policy, this is not quite possible, but we can get close enough. And we start our journey with describing the requirements of the product that we need. The first point is data presentation consists of every subscription we've got. That means we want to have those visualizations that are gathering the data across all of our subscriptions. And for those who are not familiar with Azure, the subscription is like the billing unit in Azure. Second point is that monthly costs should be close to $0. So we want to pay as little as possible. The third point is that we should keep the implementation cost on the lowest level possible. And by implementation, I mean the time that we will be spend for implementing this solution. The fourth point is that we would like to have alerting on the resource level. As you can imagine, like getting an alert for the whole subscription is not what we want to have. Rather than that, you would like to have an alert about a specific resource that is going through the roof. The fifth point is about integrating the solution with our deployment model. We have written an PowerShell abstract layer on top of ARM templates, that is infrastructure as a code in Azure. And we would like to integrate the solution with this deployment model. And the last but not least, data granularity should be on the lowest level possible. And by data granularity, I mean the interval between data being refreshed. As you can imagine, refreshing the data once a week is causing that the alert in the worst case scenario will be triggered after a week when the costs were generated. So we would like to have this window as narrow as possible. This presentation is split into two parts. First one is about gathering the data, in which I describe the method of gathering the cost data from Azure. Any other cloud providers have probably similar ways of doing this. And the second part touches the actual presentation topic, which is data analysis and alerting. Azure as a cloud provider has a wide range of services that helps you to build your application. And in order to gather the generated costs of your environment, we will be using so-called cost management API. On that slide, you can see a query endpoint, which accepts such parameters as start date, end date, groupings, and much more. And obviously, full specification can be found on Microsoft documentation portal. What's the basic concept of our application? On the left-hand side, we have the API from which we will be downloading the data. And on the right-hand side, we've got the part that we need to do. Reading from the left, we've got compute units that will be downloading the data and storing it inside the internal storage service. And then we've got dashboarding solution that will be loading the data from the storage and displaying us some visualization. How are we planning to implement that? Obviously, the API is the cost management API that I've already mentioned. As a compute unit, we chose Azure Functions because we've already written couple of them, and we know they cost very little and are quite easy to implement. And as a storage and dashboarding solutions, we chose products from different cloud provider, which is Google Cloud Platform. And the reason behind that choice will be explained later in my presentation. Let's move forward to our product's architecture. Here we've got the visualization of the process. And in the left upper corner, we've got timer function, which is operating on schedule. And in the first step, it puts a new message on the queue service. Then in the second step, the import data function is reading that message and then is sending an HTTP request to a cost management API. Then in the fourth step, the response from the API is converted into CSV file and put on the blob service. In the fifth step, the same function puts a new message on the queue service, which is then read by export data function. And in the seventh step, the CSV file is read from the blob service. The export data function is doing some pre-processing, and then the new data is appended to a BigQuery service. For those who are not familiar with Azure Functions, I will describe its product structure that we are using internally. From top, we have Azure Pipelines directory, which contains all of the templates for the CI/CD system. And then we have a documentation directory, scripts directory, which contains infrastructure as a code implementation. Then we've got three .NET directories, a single .ignore git ignore file, which is a basic file for Git control version. Then we've got Azure Pipelines, which is a CI/CD definition that uses those templates from the first directory. Then we've got Bash and PowerShell helper scripts, some basic README file, and .NET solution file. And basically that's it. Let's move on to the more interesting topic, which is the actual implementation. I've mentioned that we will be using Azure Cost Management API. And this API provides a query endpoint. On that code snippet, we've got dataset class, which more or less describes the payload which will be sent to the API. One of the most important property here is the grouping property. And that property describes the dimensions of received data. For example, we use resource ID, which is like primary key for us. And on the bottom, you've got the meter dimension, and the meter dimension explains the actual origin of the cost. So you can imagine, for example, for storage services, the cloud provider may charge you differently for reads and differently for writes. So using meter dimension, you can split that cost among writes and reads. And last but not least, we've got granularity property that is equals to daily. And here we meet one of the requirements that the granularity should be on the lowest level possible. And from the documentation, we see that the only value of that property is daily. So we are actually meant to use daily granularity, so the data will be refreshed every 24 hours. So we can't do much about this, and this is quite acceptable for us. So in the worst case scenario, we will be alerted after 24 hours when the costs were generated. Moving forward, we've got BigQuery perspective, and here we've got a single table called costs row. On the left-hand side, we've got table structure. Here we've got some basic columns, for example, subscription name, the actual cost, the cost in dollars. You've got that resource ID property that comes from the dimensions, and some other metadata such as export data and project. On the right-hand side, I've included the table information, and I've highlighted partitioning on field property. And it's important to say that Google will charge you for the data you process, and the cost of data you store is almost negligible. So it's important to optimize your queries against that table. And when we were constructing our dashboards, it appeared that most of the queries are oriented on filtering by date. So that's why we also are partitioning that table by date. And now I think it's time to elaborate a little bit more about .NET code. And here we've got authorization against Google BigQuery. Obviously, we don't want to keep our credentials inside code repo. And the solution for that is to attach those credentials somehow to a runtime environment. And as you can see here on the top picture, we are using Google SDK. And the Google SDK requires a file to be read from the disk. And then we are constructing the BigQuery service that is using this Google credential class that we constructed on the top picture. And then we are authorizing against Azure API. And here we are using a simple REST request. On lines 11 and 12, you've got a client ID, client secret variables being loaded from the environment variables. So that's how we make this the most secure as we can. One trivia that I would like to mention here is this funny library called C# functional extensions. And we were experimenting with it during this project. So what it does is basically it implements the railway programming approach, so you can make your code more functional. And briefly, you implement your logic in a so-called railways, which are easier to read and maintain. And in addition to that, you are handling your errors as a regular return values. So how are we using this? Here I've got a simple method of handling the HTTP communication. On the line number 3, we are sending an HTTP request. Then we are reading the status code of the response. And based on that status code, we are returning either result success or result failure. And then based on that result class, we are constructing those railways. So here we have get actual cost by resource method. And from line 19 to line 28, we have that railway. So we are using send internal function here. Then we are operating on the result class and using C# functional extensions native functions such as map and tab. And on the last line, we are dealing with all of errors that occurred during the railway processing. Stepping even one step higher, we have the actual Azure function logic, which is using this get actual cost by resource method. Then we are merging all pages that came from the API. Then we are converting those pages to CSV file. Then on line number 5, we are uploading this file to a blob service. And then we are sending a new message to a queue service. So that's the next function is triggered. I'm sure that this picture is no surprise for you, but I need to mention it for the record. Beside the actual logic, we also implemented a very basic CI/CD system. It consists of 2 stages. The first one is build stage, and the second one is the deployment of both infrastructure and an application itself. Going deeper to YAM definitions, here we've got build definition, and here we have that implementation of attaching Google credentials to an actual environment. So we are reading the file from variable groups from Azure DevOps portal. That variable group is linked to Key Vault service in Azure. And then that variable is written to a file called Google JSON credentials.json and attached to the program. The next point is to deploy infrastructure. And here we've got the implementation of the usage of our PowerShell abstract layer. So as you can see here, we've got a couple of PowerShell classes. For example, that functions settings class that has all of the properties required for the Azure functions to be deployed. For example, we've got app service plan SKU, we've got service kind, we've got runtime version that is equal to .NET Core. And last but not least, we are calling deploy Azure functions function that is converting this PowerShell class to ARM template, which is JSON. And then that JSON is deployed to an environment. Next, we have application deployment. So I've highlighted here a single line. We are using Azure Functions Core tools. So that's the way that worked every time for us. Apparently, there are some other methods of deploying your Azure functions, but they may not work as expected. At least for us, they didn't. Okay, I think it's time to put the boring stuff aside, and it's time to move on to the more interesting topic, which is the alerting itself. The basic concept that we introduce is that we want to know about the rising cost of each resource as soon as possible. And in order to that, we will be analyzing the cost forecast, which basically is a time series forecasting problem. And as you may know, beside the historical cost usage data, the Microsoft also provides a basic forecasting for your resources. And the first idea is about gathering that forecast using the existing technology stack. So both historical data plus forecasting is gathered by Azure Function and stored inside the BigQuery service. The second idea is to use an external forecasting model. And the major pros of this approach is that this model will be fully managed by us. In comparison, it looks like that. In the first column, we've got each aspect of the solution that we care about. In the second column, you've got idea number 1, and in the next column, we've got idea number 2. Looking from the top, we've got implementation cost, and the implementation cost is the time that we need to spend to implement this solution. Obviously, like adding an additional HTTP request is no problem for us, and writing a new machine learning model is quite a challenge. Difficulty seems the same. HTTP communication is quite easy. On the other hand, machine learning is not. The possibilities are the other way around. So the possibilities of writing our own fully managed by us model are quite high. So we can do whatever we want with this. And the cost management API forecast usage is quite narrow. So it's fully managed by the Microsoft. We actually don't know what sits behind that, and we need to use whatever they provide. And last but not least, we've got fun factor, which in the end is driving us. And we want to touch a technology that we haven't touched before and to learn new stuff. So considering all of those aspects, we chose an external model, and we planned that we can make a room for a couple of more days for that project. But the most important fact is that we will learn something from this, something new, right? Moving on, we made a quick research of the market, and we found 3 possible implementations of the external forecasting model. The first one is the Python scikit-learn, which is a popular ML framework, but on the other hand, it's relatively hard to implement a new model with this one. And what's the worst part is we need to introduce a second language, which we don't want to do. The next solution is Azure Machine Learning, which is easy to implement. It fits into our current technology stack, but it requires additional resources and the costs are quite high. Last but not least, we've got BigQuery ARIMA model, which is like the forecasting model managed by the Google Cloud. It is easy to implement. It fits into our current technology stack because we chose like Google BigQuery for our storage and Data Studio as a dashboarding solution. And after some tests, it came out that the costs of that solution is the lowest from those 3 presented. So from our perspective, the BigQuery ARIMA model is the most complete product, and we decided to keep going with it. As I mentioned, this model is fully managed by the Google, and the name translates into autoregressive integrated moving average. It requires some basic parameters to start working, and it is almost a black box for us. For the record, we are not data engineers, so we have very little knowledge about the machine learning models. As you can see underneath the model, there are quite many modules that are implementing the overall experience. But frankly speaking, we don't need to know everything about this. Here we've got the example of working ARIMA model. The blue line is the time series that we analyze. The orange one is the forecast. And the yellow one is the seasonal trend, which in that case, it's the way the time series varies across the week. When we zoom into the forecasting part, it appears that there are 2 additional lines. One is slightly lighter blue, and the one underneath the time series is the pink one. Both of them are the bounds of the forecast. So we've got the slighter blue one, which is the upper bound, and the pink one, which is the lower bound of the forecast. It's important to say that the ARIMA model has the parameter called confidence level, which is expressed in percentage. And the bigger confidence, the more those lines are spread apart. In other words, if you want to have 100% confidence in your forecast, the ARIMA model will print you forecast that will be surrounded by minus infinity and infinity. So you need to keep that value in check. So we are using, like, as far as I remember, 95% of confidence, and that's quite fits our needs. I've mentioned that ARIMA model implementation is quite easy. Here I've included all possible parameters when creating a new model. Apart from the most obvious ones, such as dataset reference, we've got horizon. That is the horizon of the forecast expressed in days. We've got data frequency. In our case, it would be daily. And we've got also holiday region that takes holidays into consideration, which in our business is quite important. Here I've got a graphical representation of the ARIMA model from the BigQuery perspective. On the left-hand side, we've got Azure API, which is cost management API. And in the first step, we are gathering the data from the API, and we are putting the data into costs row table. And that process was described in the first part of my presentation. In the second step, we aggregate the data and filter out some records that we are not interested in. And we transfer the data to a new table called costs curated. Then we are creating a new model, which is separate object in BigQuery. In fourth step, we are copying the forecast to a new table. And two last steps are about merging the historical data with forecasting and putting those results into a new table called costs enriched. From the dashboarding solution, it looks like that. This is actually actually the real dashboard that we are using, and I've cleaned up the names due to our security policy. In the left bottom corner, you can see the forecasting chart. It is a simple chart that is meant to show us that the prediction algorithm is working as expected. The blue line is historical data, and the slightly lighter blue line is forecast itself. Those two spikes are probably virtual machines reservation or something like this. And if you take a look on the blue line and the slightly lighter blue line, those are on the same level, which means that the forecasting works as expected. Okay, so now we discussed the data gathering and the cost forecasting. And I think that it's time for the alerting itself. Actually, alerting is based on the time series forecasting. Alerting based on the time series forecasting is called anomaly detection. And here we are detecting cost offenders. And by cost offender, I mean the resource that is using more money than it should. And the idea here is very simple. We compare the actual usage of that resource, let's say for today, with the forecast that was calculated the day before. So let's say the forecast was calculated yesterday. And if the actual usage is greater than the upper limit of the forecast for some amount, we are marking this resource as a cost offender. So if you look at that query from the BigQuery, you've got two thresholds here. those thresholds are on the lines that begins with end. So firstly, we've got exceed forecast percent threshold, which is a relative difference expressed in percentage. And then we've got exceed forecast diff threshold, which is expressed in the actually euros. So this is the absolute difference. The whole process of the cost analysis is orchestrated by the Azure functions, which are executed on the trigger. Firstly, we've got functions that function that is refreshing the model, then the function that is meant to merge the data. And the third step, in the third step, we are getting the offenders and sending an alert to one of our Slack channels. And that Slack channel is monitored by us every morning. So how this alert looks like. For example, on the top picture, we've got the alert from 20th of December last year. And here you've got an application insight resource that exceeded its forecast by almost 20%. So when we receive that alert, we are obligated to take some actions to investigate this a little bit more and to learn what's the origin of that unplanned cost. And on bottom, you've got the report from the next day, when we had no offenders at all. And on that occasion, we see this happy panda face. You may wonder, what are the costs of this solution? We discussed quite a lot of parts of the system. And firstly, I would like to introduce some background for that. Currently, we are running 6 subscriptions, which contains almost 1,500 of resources. We are gathering 100 megabytes of data per month and storing more than 1 terabyte of overall historical data. So the costs are following. Azure Functions cost 14 euro cents per month. Azure Storage costs 40 euro cents per month. BigQuery Storage costs 45 euro cents per month. But apparently BigQuery Analysis, so this is the price that we pay for the forecasting, costs 37 euros. So this is not quite close to zero as we may want to be, right? So we need to optimize it further. And the optimization that we found was switching the refresh of the period of the forecasting model from once a day to once a week. And that way we lowered the cost BigQuery analysis price to 5 euros. So it sums up to slightly more than 6 euros per month for the whole solution. So for us, it's enough, and it is enough close to zero as we wanted at the beginning. So what's next? One of the requirements was to integrate this solution with our deployment model. Here we've got on the left-hand side a class in PowerShell that contains metadata that is required for all of the resources that we are deploying to the cloud. And one of the property from that metadata class is a team property, which is translated into tag in Azure. And we would like to download this information and save it in the BigQuery service. So when the new alert is generated, the proper team is also mentioned, and that team is required to take some actions and to manage their resources and to optimize the cost of it. So we don't have to pay any additional attention to that process. The more brutal approach is that giving very high differences between forecast and the actual usage, we may want to trigger a PagerDuty alert or even disable the network access by switching off the private endpoint or deleting the DNS record. Probably doing so on the production environment isn't a very wise idea, but lower environments won't be hurt as much, and frankly speaking, they are much more prone to an error than the production one. I think that's it for that presentation. And yep, we are recruiting. And if you are interested, please contact us after the presentation. Thank you for your attention, and let's go back to the studio.